the simple pendulum. A simple pendulum is an object of mass m that is attached to a massless, rigid string of length L and removed from the equilibrium position and then released. The object is moved such that the wire makes an angle theta with the vertical. This angle theta is small. A small angle means sine of theta is approximately equal to tangent of theta and equal to theta in radians. An angle up to 15 degrees or so can be considered a small angle. Once released, the object will come back towards its equilibrium position. It will not stop because of inertia. It will go on the other side and it will come back and it will execute a harmonic motion. We'll see in a minute that this is a harmonic motion. Let's find the restoring force. The weight of the object is W, which we can decompose into a component along the wire and the component that is perpendicular to the wire. Yes, that will do it nicely. So this will be Wx. Wx from simple trigonometry in this picture, in this triangle, will be W sine theta or mg theta, in which we used the small angle approximation. But this is a restoring force akin to negative kx in Hooke's law, so we're actually writing it as negative mg theta. On the other hand, we know from rotational motion that the torque is equal to I multiplied by the angular acceleration. And we recall from circular motion what the angular acceleration is. If an object travels a distance s and sweeps an angle theta, the relationship between the two is s equal r theta. If we take a first derivative, ds dt will be r d theta dt. And if we take a second derivative, d2s dt2 will be equal to r d2 theta dt2. This being the angular acceleration that we need here. On the other hand, the moment of inertia of a particle is mr squared. In our case, r is the length of the string. So the moment of inertia of our object, which is a point, it is a particle, is ml squared. Now if we put everything together, let's see what we get. The torque is minus mg theta, the force, multiplied by the distance between the force and the pivot. In this case is L. The moment of inertia of the particle is ml squared. And alpha, angular acceleration, is d2 theta dt2. When everything is put together, we have minus mgl theta is equal to ml squared d2 theta dt2. The mass cancels out. 1L cancels out. So we are left with d2 theta dt2 times L plus g theta is equal to 0. Or rearranging the terms, d2 theta dt2 plus g over L theta is equal to 0. We saw that any time we have an equation that looks like this, first of all, it is simple harmonic motion, and secondly, the period of the oscillation is 2 pi over omega, whatever this omega turns out to be. This is how we got the period of oscillation of a spring to be 2 pi square root of m over k. If we look at our equation, it looks like that. So d2 theta dt2 plus g over L theta is equal to 0. We call this omega squared. Omega squared is g over L, which means the period will be 2 pi over square root of g over L, or the period is 2 pi square root of L over g. An interesting result is that unlike the spring, the period is independent of the mass. It depends only on the length of the pendulum and on the acceleration of gravity. And it is a simple harmonic motion because the equation of motion satisfies the conditions for simple harmonic motion.